Thank you very much. So I heard some of this. I'm Josh Vaughn. I'm from the Department of Mechanical Engineering at the University of Louisiana at Lafayette. So the next few days, we're going to be talking about what I've titled as modern approaches to system dynamics and controls. The first part today, our first kind of 1 hour or so, I think we're going to get an intuitive look at kind of high-level understanding. And the next 2 hours, a little bit of a review just to make sure we all understand and are on the same kind of page moving forward. Then tomorrow, we're going to talk about a technique called input shaping. It's a very good vibration and controls technique. And then on Thursday, the 3 hours there, we're going to talk about some more modern control methods. And then also look at some machine learning, a reinforcement learning-based control method that my lab's been working on a little bit as well. So I thought I'd spend the first few minutes today just telling you a little bit about me and where I come from. So maybe I can convince you to trust me when I'm teaching you these things. I know a little bit about me. So I'm from Southern Virginia in the United States. So the state of Virginia is over here. So Washington, D.C. is right there. So my house is probably the same distance from Seoul to Gumi from Washington, D.C. to my house. So from this part of Virginia, went to a really small school in Virginia. This is pictures of my campus, the college I went to in Virginia. And I was actually a physics and applied math major as an undergraduate. So double majored and played baseball. College sports, as maybe you know, is really kind of big deal in America. So played baseball for 4 years there. I went to graduate school at Georgia Tech. I worked for Professor William Singhose. So the input shaping idea we're going to talk about tomorrow primarily. Dr. Singhose was one of the leaders in this area, or has been a leader in this area for quite a while. So worked with him, master's degree 2004, and then a PhD in 2008. After that PhD, I actually did a postdoc in Japan for 1 year. So worked in Japan for a year. Then went back to Georgia Tech for a couple years as a research engineer. And then started working at University of Louisiana Lafayette in August of 2012. So I've been in Louisiana about 5 years. If you're not familiar with where Louisiana is in the United States, here's our map of the U.S. again. Louisiana is down here near the Gulf of Mexico, or on the Gulf of Mexico. So probably the most famous city in Louisiana is New Orleans. Kind of really famous for jazz. This area of the country is also really famous for delicious food, as we'll see. A lot of our students, so this region, the Gulf of Mexico, has quite a bit of oil. So a lot of our students will go work for oil and gas companies and energy companies. So it's a big sponsor for some of our research as well. Within Louisiana, we're in Lafayette, which is right here. And you'll see it's about 3 hours over to New Orleans, again, the most famous city. And then 3.5 or 4 hours over to Houston, which is also a fairly large city in terms of the U.S. So I'll give you a little bit larger map. We're, again, right here in the south central of Louisiana, only 30 or 40 kilometers to the Gulf of Mexico. But it's kind of, there's no pretty beaches here. This is all swamp, actually. So it's a big part of that. We're actually the center of what's called the Acadiana region of Louisiana. And it's called that because of this Cajun culture. So these Cajun settlers in America, we actually went to Canada first from France. Then were kind of kicked out of Canada and came to America. And when they came to America, they came and settled in this region. So this entire region of Louisiana, this southern part of Louisiana, has many, many people from France, basically, of French descent. They've been there 100 years or 200 years now, but many people's family names are French. Their ancestors are French. So again, Lafayette's right there in the middle. So Cajun, basically mainly from French, but then also mixed with some Spanish settlers in that region as well, Native American Indians, and then also some Africans that were brought over as slaves, unfortunately. And again, actually, many of the settlers are French. Most people's grandparents, most of my students' grandparents, well, not most, a lot of my students' grandparents will speak French as their first language, actually, and English as their second language. So many of my students will speak French as a second language. Our region of the U.S. is known for kind of good food. One of the most famous dishes is called gumbo. Looks something like this. It's pretty good. It's kind of like curry, basically. It's pretty good though. So some rice with soup, basically. Another famous dish is crawfish. So these are crawfish. This is a popular way to eat kind of boiled crawfish. So if you don't know crawfish, they look like a miniature lobster, basically. And you just eat the tail. So it's actually pretty good. So you'll see that. My university, we have about 18,000 students at our university, most of them being undergraduate students. I mentioned the southern part of Louisiana is a kind of swamp area. This is the middle of our campus. In the middle of our campus is kind of a pond swamp area, natural habitat, and there are actually alligators in the middle. So if you look at this picture, maybe a little bit hard to see, but there's one right here, right in the middle of our campus. It's actually a pretty kind of nice area, especially in spring and fall. It's very pretty. And they don't get so big, so they'll get maybe the size of this table. And if they get too big, then someone will come and take it away. But they're kind of cool to go see. As I said, sports is really big deal in American colleges. So our football team has a pretty nice stadium as well. So it's our football stadium for a game. Okay, so I'll give you a little bit more information about the kind of what we're going to talk about. All my notes, everything we talk about, you notice I have 2 microphones on. At least one of these audio recordings will go with the notes and get posted to this top web page here. So I'll post all the notes. There's also a lot of information there already about what we're going to be talking about. Some supplemental information. I'm going to have example code. So we'll look at some code in class, but there'll be a lot more example code for you to go look at and run if you're interested in. My email address is here. And then I have a Twitter account I use for my kind of lab information and things like that. If you're wanting to follow, feel free. And if you're interested in more, we'll talk about some of my research throughout the 3 days. If you're interested in learning more about my research or my university, this is my kind of lab's webpage. I put this on every class I teach. I put this slide. I'm going to ask you guys to be responsible for your own learning. What that means to me in a class like this, if you have some questions, please don't be afraid to ask me. Okay? And in fact, I'm going to ask you a lot of questions, and hopefully you have some answers. All right? So ask me questions as well. All right? And this is maybe doesn't apply so much here, but I was a pretty bad student, actually, when I was a student. I could memorize many things, but didn't do a good job learning things until I got to graduate school. So I always encourage students to be better than me. Actually try to learn the material. Don't just memorize some technique or something. Okay, so that's me. Let's get started. Let's see, I can do this. Just make that black for now. And screen up. Okay, so again, I'm going too fast, stop me, ask questions. I'm going to ask you questions, all right? So I want kind of some conversation, especially this kind of small, short class. I'd like to start right now talking a little bit about an introductory example. So let's think about our intro example. And let's talk about a pretty simple system, but I think it's going to give us some intuition, some understanding of how things work. I'm going to take just some mass, M, and it's on a frictionless surface. So let's represent that by some wheels, as you probably have seen in textbooks, etc. And the position of this mass, let's call X. All right, so pretty simple so far. I'm going to say we have some control force. So we have some control input U, and then maybe there's some disturbance to the system, some force that's trying to keep us from going where we want to go. Right. And the objective for our system is going to be, let's write that, kind of our goal. To move our mass m, the position of our mass m, defined by x, to some desired location xd. Okay? Or put another way, move my mass to a desired location. I want to take m and pick out what u needs to be to move it over here. All right. Everybody with me so far? Yes? Yes? Okay, good. Okay, so let's start out. I think it's pretty easy. We can, Mr. Newton tells us that, right? We're all on the same page. Some of the forces, U minus F. And we have a pretty simple equation of motion describing our system. So for now, let's start out, for now, let's ignore we don't have any disturbances. F is not there anymore. Okay, so again, pretty simple so far. Okay. So I want to move, I need to pick my input u for all time to move mass towards some desired position xd. How should I do that? Who has ideas? Input some force? Sure. What should that force look like? Any idea? That's what we're learning about, of course, I know. Okay? So if you want to drive your car or drive some bicycle or something from one place to another, what do you have to do? Straight line. You're going to put on the gas, right? Accelerate until you get close to where you want to go, and then put on the brakes to decelerate. Maybe we should do something similar with our force, right? Force equals mass times acceleration. We can kind of think about it the same way. Right? So let's think about our first approach, maybe. And we're going to have time on that axis, and then maybe our control force here. So if I'm going there and I don't have any limits on how fast I can go, I want to accelerate as long as I can, actually, and then step on the brakes as quickly as I can. So what that's going to look like, let's say this is time 0, just to give us some space away from the axis. At time 0, I'm going to start accelerating, and I'm going to accelerate as hard as I can, or put as much force as I can to start out with. I want to get there as fast as I can, right? So immediately, I'm going to ramp up my force to as hard as I can push on this mass. Okay? And I'm going to do that as long as I can. Okay? And then when I get close to my target, and I get closer to xd, I'm going to decelerate. I'm going to pull on it to stop it as hard as I can, right? So that's going to look like is something like that. And what we've drawn here, we kind of assumed to make this plot look symmetric, we've assumed that I can decelerate, or I can have negative force at the same peak as the positive force. Right? So, okay, we have some command. flashing, of course. This kind of command, so this guy, you'll see called a bang bang input. So I bang on as hard as I can and I bang off as hard as I can. So bang, bang. That's what you'll see this called. All right. So if I'm going to design this force to move that mass, what do I get to choose as a controls engineer from this kind of profile? Proper times, right? So Umax is probably set for me by the physical system I'm trying to control. Whatever force I have some limit on that. I don't have a lot of control over that usually. But I do have control over picking T2 and T3. And we're saying basically kind of defining by kind of definition that whenever my command starts, I'm going to call that 0. So T1 is always 0. All right. So, how do we pick those times? Well, we have some equation that tells us the relationship between this profile and the acceleration. Right? And then I know the acceleration is related to the position in some way. Right? So basically I can write rewrite my equation of motion that way. And then I could do something like this. Just integrate that twice. I just have a curve. Take two integrals, and it's actually squared there. And that's going to give me some answer for T1 and T2. Okay. And that's not so hard to solve, but I actually can take some shortcuts to get to some answer here. What do we know if this is symmetric? How far do we get by time T2? So I know that my maximum force is this kind of the mirror of my minimum force. What? Symmetric. Yeah, it's symmetric about 0 force. Right? So if I have a symmetric maximum force, how far have I traveled by T2 in terms of my total travel? Half as far. Right? Everybody see that? So I'm accelerating half as far by T2. So what I know is that those two areas are equal. So that's going to tell me that I get to some velocity and then right back down to 0, which we'll see in just a second. So I actually can simplify this integral a little bit. I take that integral and I know that by time T2, because this is symmetric, I better be halfway to where I want to go. Right? Okay. So, let's see. I'm going to take this with me to write this part. I'm going to solve that integral. So just work out the integral. A few more steps in between are in the notes, so you can check it out. So basically, by solving this integral, I know what T2 needs to be. Okay. And I have some kind of acceleration ratio here from the maximum force to the mass. So basically, I want to accelerate as fast as I can and then decelerate as fast as I can. It's kind of what this is saying. So if T2 is that, what do we know about T3? Yeah, it's twice T2. Right? We say we have to get halfway by T2. We know these are symmetric, so we know that. So let's look at this a little bit more graphically. I think will help us also understand. So we get some answer for what these two are. Those times, that's useful. Let's look at this as a plot. It will help maybe us understand a little bit more. So I'm going to draw another axis there, and then one more there. Okay, so I've drawn up two other sets of axes now. Drawn up velocity and position. So if I'm issuing this force command to this mass, what's the velocity look like? So let's think about the velocity in this segment of the plot. What's it look like? Yeah, it's just a triangle, right? So if I accelerate, if I have constant acceleration, my velocity is just linear, right? So I get up to some, blue to match. So maximum velocity, and if I have a constant deceleration, that means the slope of this line is constant, I get a straight line, right? That should be a straight line, sorry. Okay, what's position look like then? Goes and comes back. Well, hopefully not, because that's not what we want, really, right? It's going to increase. Hopefully it gets to xd at some point. That's where we want to go. It's like an S curve, kind of, right? So we have some acceleration. The slope of that line here is increasing to there, some inflection point. So I'm going to where xd is where we got to. All right. So that's a pretty good response. If I just have this mass and nothing else is really bothering us, we can get to where we want pretty quickly. This is the fastest way you can get there, these bang bang commands. All right. So let's ask a question about this. What are we missing? Well, we made some kind of critical assumption back over here. We said we don't have any kind of disturbances acting on our system. So then the question what if we do have some disturbance now? Does this work anymore? Of course not, right? Well, it can work, but we have to know what the disturbance is. So we're kind of assuming we have some force is acting on our system and we don't really know it. Right? If we know what it is, we can kind of work it into this and be okay. Right? It's not as easy, but we still could use the same idea. So if we have some disturbance force, so let's do, say the blue line was with the force, and let's say we have some disturbance now. So at this time, maybe there's some disturbance force there, right? So actually, let's move it, some kind of constant disturbance force there. Well, what's going to happen is, no disturbance yet, and then maybe goes off track, right? There's many, many ways that can happen, but I get to where I want to go, and then suddenly there's something pushing on me, pushing me backwards. Right? So this kind of controller, this bang bang command, what we would call an open loop controller. We're not using any kind of feedback. We're not measuring where we are. We're just kind of using the physics of the system to try to get to the right place. Right? So we have some problem now, right? So let's say, or let's look at error. Our steady state error. So the error between where we are and where we want to be in kind of the long term out here is no longer zero if we have some external force. So that brings up a good question. Our controls engineers, we need to get M to where we want it to be. How can we do better? Oh, you guys have some ideas. Don't be afraid. So I want to get mass. So again, our goal is that. Right. So that's correct. Sure. I think you're on the right track there. So I think what half step further than what you're saying maybe is to use some measurement maybe of the error to understand what the force needs to be. Right? So if I define, let's see, some error signal. There's a difference between where I want to be and where I am right now. Right? So if I do that, maybe I can change some things around a little bit. Okay? Well, maybe I could say, let's see, second approach, let's say. So if I have some measurement of this error, okay, or some just measurement of x, the position of the thing, there's some things I can do. Well, maybe one kind of easy way is rewrite that a little bit neater for you. Maybe I have some kind of inequality. And if x is less than xd, and I want to go over there, I need to start accelerating. And then if I get past a little bit where I need to be, I need to start stopping. Right? And maybe I could tune this to not be xd, but it could be some other number around there, like that. Maybe if x is less than xd over 2 or something like that, or if it's greater than xd over 2, I could play with those numbers. But the idea here is kind of based, we'll call this maybe you might call that switching control or on-off control. This is how your heater or air conditioner actually works. Right? The temperature is too low, turn on. If it's too high, turn on the air conditioner or whatever. Right? So kind of switching control, on-off control, it's kind of one of the most basic ways we can do that. Well, what does that do for my response? If I have this kind of switching controller for this kind of system, what kind of position response do I get? Yeah, it's going to be oscillatory. Just like your temperature in your room for your heater, right? It's going to go up and down a little bit always, right, when it's switching on and off. So you may get to the right position, too black. But most often, you're going to oscillate around it. And this can account for if you have some force that pushes you away from XD. Now your controller is saying, oh, I need to turn back on. Whereas we didn't have that before. Okay? So there's the next kind of first simple controller. But we're still not really getting to exactly where we want to go. We're getting closer maybe now. And we have some measurements and a correcting for if there's problems. But what we want to do. Can we do better, I guess is the question. The answer to that is yes, we can do better. So the second question is, how can we do better than this switching controller? Let's call this our third approach. So how can I do better than this switching type controller? Acceleration is lower. Oh yeah, so maybe I could approach more slowly so I don't go so far over before I stop. That's one idea. Well, we had some measure of error, right? So what if I maybe picked my force that's proportional to that error in some way? All right? So maybe let's try that. Okay? So I have some. I'm going to say, hey, make this force. I'm going to measure where I'm at. I know where I want to be, xd. And how hard I'm pushing on the mass or pulling on the mass is proportional to that error. Okay? How well is that going to work? Well, let's look at what's going to happen. So I'm going to draw, to start out with, this plot. This guy won't be. Okay? And then we're going to say that's xd. That's where we want to be. My mass, however, starting out at 0, let's say. That's my starting point there at 0. Okay? So at point 0, I have Kp times xd, that part's 0. Right? So I have some kind of large force, depending on how big I pick Kp to be. Right? So at time 0, I'm going to have the largest force I have for all time is going to be there at 0. Right? And that height is that tall. Right? Because initially, I'll write this up. We just have that. Okay, so I start pushing on the mass a little bit. So it starts moving. What's happening to the force now? It's going down, right? This error has reduced now. So this force starts coming down. Right? But the mass, I'm still pushing positive, so it's still going. What's happening to the force? Still going down. Right? But even though it's a little bit smaller, I'm still pushing forward. Still moving forward. Until x equals xd there. So what's the force at that point? 0, right? So we know that it has to get 0 there. Okay? And now, up here, I'm going to have non-zero velocity when I get there, actually. So now what happens to the force? We have x is greater than xd. Anybody? X greater than xd, it's negative, right? So you start actually pulling on it. Yeah, so it's below 0. So that's going to start slowing this mass down. All right? And it starts getting, so you're pulling on it. There'll be some maximum out here. And then eventually you'll start pulling it back towards xd. For this kind of proportional controller, we call, you're still going to get back to xd and have a non-zero velocity when you get there. Right? So you're going to go back this way. Then you're going to need positive force again to push you back to xd. Right? So this proportional controller alone is not really helping us so much. Right? Tune this way. What happens if I make, maybe, okay, well that maybe work. Well, why can't I just make Kp larger? So I'm pushing on it harder. What does that do to this response? So let's do some kind of low number for Kp there. Right? What if we do in red, Kp is some large number? What does that change about this response? Well, we know this is still going to be true. This peak is still Kp times xd. Xd hasn't changed. Now Kp is much larger. So this spike is much larger. What does that mean for how quickly the mass starts moving? Yeah, so I'm pushing on it harder, it's going to accelerate faster. So we have the same kind of trend, but what's going to happen actually, because I can push harder, or I am pushing harder based on the error, right? If Kp is larger, actually I'll push back and forth faster. Right? So the response looks something like that. And there's a nice, pretty version of this in the notes. So this guy, this kind of controller, is called proportional control. Okay. So we're going to keep talking, and throughout this time we'll talk about PID control. This is just the P part of PID control. Okay. And for this system, it leads to an oscillatory response. It's the best you can do with just proportional control. Okay. So if that's the case, let's see, let's get rid of our second approach. Maybe keep trying some things. It's going to be, what, our fourth try at this? What can I do now? I'm going to get you started. I'm going to say, well, I think that started to work okay, right? We kind of have a good idea here, I think. We're going to measure where we're at, measure where we want to go, and do something based on those measurements. But we need to do something else, I think. I heard a couple of people say, I think. What can I do? Any ideas? Well, what was the problem with just this proportional control? The problem with just proportional control is when I got to position, the position I wanted to be, the velocity part wasn't right. Right? I got there and I had non-zero velocity, so my mass kept going too far. So maybe I want to include some kind of velocity term in my controller too. Right? So maybe I can look at, remember, my desired position, desired location, kind of embedded in that is I want x equal to xd, right? Another way to write our goal. We definitely want x equal to xd, but we also want my velocity to equal the desired velocity. And in this case, because we're saying, hey, that's a fixed position, well, maybe we want it to be 0. So we get to the position we want to be at, and we're 0 velocity now. We're going to stay there forever. Right? So maybe I can define some kind of error for this term too. Right? And if I look at the error I defined, I just take its derivative, we get some kind of measure of the velocity error. So maybe I want to do something, I'm going to propose that we have some kind of term in our controller that generates force proportional to the velocity error. So we have one term based on the position error and one term based on velocity error. So we want to get to our final position with 0 and be 0 velocity when we get there. Okay? If we expand that out, get something that looks like that. Okay. So this fourth approach, is proportional plus derivative control, or PD control. All right. So I have some part of our controller that's proportional to the error, and some part of the controller is proportional to the derivative of the error, PD control. Okay. Well, let's look at the same plot for this guy. I'll make it a little bit smaller this time so it'll fit. Needs to be symmetric. Okay, and let's times 0. And we're still going to start from 0. Okay. So what does our force look like now? So time 0 is sitting there, waiting to start moving. We look at our two terms of our controller. Well, we still have the proportional term part. This error is going to be the same as it was before. At time 0, does KD add anything? The derivative part of this controller? Well, the desired velocity is 0. And we say I'm starting at rest. I'm not moving at all. So x dot is 0. There's actually no derivative error at time 0. Right? Yeah, so it's the same thing. So the first part is still kpxd. Okay? And then our system starts moving a little bit. All right. So now we can look at the two terms again. This term starts shrinking. Right? But what happened to this term? It actually got bigger, right? So xd for this case, 0. So now we have the derivative part of the controller trying to tell you to give less force. Start stopping. Right? So you actually have what's going to happen compared to that one, this actually goes down faster. Towards 0, right? So this response is a little bit slower. We go a little bit further. Same thing kind of happens, right? The error is getting smaller, but we're going kind of faster. So this derivative term starts to kind of add more and more into the controller and determine what U is, contribute more to what U is. Okay? And if we've done a really good job, when we get there, we might have no error. We might have just a little bit. Okay. But the velocity controller, the velocity part, is going to do that for us. So with this controller, that KD term serves to get you to XD and make the velocity match. So you get a response that looks like that. You can make a larger KP or KD, and actually what the kind of big question then is if I have this form of controller, how do I pick what KP and KD should be? And that's one you can spend the rest of your career working on, actually. for a variety of systems. Right? And even for really simple systems, there's some kind of heuristic ways, and some you can solve some optimization problems. There's many, many ways to do that. And we could talk about that for the rest of the spring if you wanted. Okay. Okay. So, how do I pick KP and KD? That is one of the fundamental questions of a controls engineer and controls design. How do we pick the control gains? Right. There's another way to say that. These KP and KD are called control gains. So those control gains dictate how much each term contributes to the overall control. Right? And we'll see, even for more complex controllers we'll talk about, you see the same terminology. The kind of various terms in your controller have different constants associated with them that tell you how much that term contributes. So let's look, before we take a little bit of a break, let's look at this guy and think about, well, actually this whole approach so far, we've still said F is 0. What happens if I have some disturbance force now? Do these guys fix that problem? Do these help you? If there's some force, I move my mass over here, and I have some good controller, and we get to where we want to go eventually, and someone comes up and pushes on it. Does this controller get you back to where you need to go? Maybe not. Okay. Well, let's think about what's going to happen if I have some disturbance force F now. All right. So I get to some position. So let's do, I'll plot up here. All right. And let's say I get the whole beginning part is no problem. And maybe I get to kind of where I want to go. All right. And then somebody comes up and pushes on my mass. Okay? Well, what's going to happen to the position? I have some force and I push it really quickly. What's the mass going to do? Yeah, it's going to start moving a little bit. So in this case, force is positive, so it's actually going to go in the positive direction. So we get some little change like that. Well, what does the controller start to do? Now I see, well, hey, x is not equal to xd anymore. Right? So I'm going to have some input force that says, oh, you're not where you're supposed to be. Right? So I'm going to start pushing you back. Right? So in this case, so this whole part was the same. In this case, right, it's positive, so I'm going to have the controller is going to try to start correcting that. Right? It can't do it instantaneously because it has to measure some error first. Right? So there's some kind of peak there, and then it's going to do something similar. Right? Like that. So this PD controller not only helps us design how to just move it without any problems, not anybody pushing on us, it can help us to counteract disturbance forces as well. Because we're able to measure what's happening with our system and adjust our controller in some way. Okay. One more thing to look at, and we'll take a small break. Let's keep that one up. We can get rid of this one. Oh. So what we had, so let's just say again for right now, let F is 0, so don't worry about that right now. Well, let's write the equation. We knew that was our equation of motion for this system. And then we said, well, that should be that's what our proposed control equation of motion, including our controller, looks like. Does this equation of motion look familiar to anyone? Let me draw up a system and tell me, and we'll talk through. Okay. If I'm going to write the equations of motion for this system, right, I can draw my free body diagram. I have forces from the spring and damper, right? So I know that well, what's the force from a spring? I know it's just proportional to the change in length of that spring. All right? And I know the force from my damper, my dash pot, is proportional to the rate of change of that length. All right? So my PD controller is mathematically equivalent to placing a spring and damper between my desired position and the actual position of the system. Okay. And I think this is a really helpful way to think about PD control, even for more complex systems. You're basically putting this kind of virtual spring and damper between where you want it to be and where it is. And then by picking Kp and Kd, you're effectively picking the natural frequency and damping ratio of that kind of mode of the system. This one really helped me when I kind of started understanding this for PD control. Okay. Questions about any of that so far? So we are 2:30 right now. You guys take about a 10-minute break. Come back at 2:40. Okay.